This is module number 5 from my online Introduction to Tensors for Non-Mathematicians course or set of videos. This module will formalize our understanding of the covariant basis transform. Now, we've already worked with this. If you remember from the introduction, we used that matrix to describe how the observer's point of view rotates with the sloping or the gradient of the land, and so that was an example of a covariant basis transform. So we want to describe that transform as well as describe how appropriate transformations may be applied to both the basis and coordinates of a tensor. Now, so far we've only talked about primal vectors, so we'll predominantly rely on that as the example of a tensor. Now, we want to do that. We want to apply these transforms such that the fundamental value of a tensor is preserved. And if we go back to our lecture on the formal definition of a tensor, we want to apply the transform such that the tensor is invariant to change of basis. As the course title suggests, these videos are aimed at scientists and engineers with some background in linear algebra who want to learn more about tensors. This module defines the forward transform of a covariant basis set as well as its inverse. We call that the backward or reverse transform. We also describe how appropriately corresponding transforms may be applied to the coordinate or coefficient arrays of that tensor. I have written a text to accompany these lectures. A link to that text will be provided in the description below when it's available. Still working on that. If you have any questions or corrections, please place them in the comments. I'll try to address them as quickly as I can. As always, please like and subscribe to see more engineering and general STEM educational videos. Let's discuss how forward and backward transformations may be applied to both basis as well as coordinate arrays. So, we've already defined a forward transform matrix, and we did so in the introduction section that was associated with our example. And what we did was we defined the rotation of the observer's point of view, and we represented that as a forward transform matrix, although we didn't, at least not as far as I remember, we didn't specifically use that term. And so this took us from what we call the pre-transform to the post-transform basis. And essentially, this section is going to seek to formalize that process. So we don't have to rely on that example as heavily. Let's consider two primal basis sets as shown below. And we are concerned with this mapping here. So we are trying to map our basis from the pre-condition to the post-condition, or we're trying to map from B sub pre to B sub post. And this is notation we're going to use throughout the text as well as throughout these PowerPoint presentations or throughout these videos, where generally we refer to values before a transform using the subscript pre, and then after a transform using the subscript post. So what do we have here? We have two sets of basis. One is pre-transform, one is post-transform, and that's indicated by their subscripts. Now, all of the sub-elements here employ subscript type indices. That's because we are dealing with column number 1, column number 2, right? We're moving from left to right. And so that means we're dealing with a covariant index, a column index, and so it is a subscript. Now the same applies down here to the post-transform set, the only difference again being this post ID. Now the forward transform is shown right here, and it's a pretty straightforward equation. We have B post is equal to B pre, sorry, didn't really have space there, times some forward transform matrix. And I am going to put pre up top and post down below here. Now, actually, let me go to this blank slide to show a little bit more clearly. So we have B post, if I can write it, is equal to B pre times F pre post. So we have our post-transform basis, our pre-transform basis, and then we have the forward transform matrix. Hopefully these subscripts, we already understand why they're there. Where does this superscript and this subscript come from? Essentially, up top, as far as the notation we use in these presentations, up top we place the before basis ID, where I call this the basis ID right here, and then below we put after. So this would be the ID we use after the transform. So let's write another example of this equation, but without using the words pre and post. So let's say I call one set of basis, I'm going to call it B1, okay? And then I have another set of basis that I am going to call B after 2. So we're using names that differ from those up above, just to demonstrate. So using that notation, my notation, our notation, again, you may not see this in other texts, the forward transform matrix would be F1 and then with a subscript after 2, right? Where this corresponds to that and that corresponds to this. So really more of a notation thing, as more than anything else. So we may define a matrix, which again is F pre-post, because that's what we name our basis, which maps the pre-transform basis to its post-transform counterpart. This is the forward transform matrix for covariant change of basis. What does this part mean right here? Essentially, the forward transform matrix is defined by this equation, which is in turn a covariant change of basis equation. So the name makes sense. It fulfills this relationship right here. B post equals B pre times the forward transform matrix. Now what we'll see when we start discussing forward and backward transform matrices, we haven't introduced the backward transform matrix yet, but hopefully you can kind of infer what that's going to mean, right? The backward transform matrix is simply the reverse of the forward. What we're going to see is that these names are largely trivial, and the superscript and the subscript here, pre-post, can be a lot more, at least in my opinion, can be a lot more descriptive with regard to exactly what kind of transform we're trying to perform. So again, the phrase for covariant change of basis tells us that this transform is defined by its application to a covariant primal basis set. And so here is that equation again, although I'm pretty sure we've already covered this in depth. All right. Now, as we said a second ago, the backward transform matrix is the inverse of the forward, and generally we will reverse the superscripts and subscripts. So if I have something that is F pre-post, one would assume that that's a forward transform matrix that takes us from the pre to the post transform basis. The inverse of that would be a backward transform matrix, and you'll see I will switch the superscripts and subscripts. So the notation that I use, you always, regardless of whether it's a forward or a backward or reverse transform matrix, you always end up with the output ID on the bottom and the input ID up top. Not much to say here. The way that we index the backward transform matrix is similar to how we index the forward transform matrix. We have our contravariant and our covariant indices, and you apply the transform in a very similar way, where we have B pre is equal to B post times backward transform matrix post pre. Now, what do these basis transforms mean practically? Physically, This transform captures changes to the perspective through which a tensor's properties are observed, and this largely relates to the example we used in the introduction video. With regard to tensor analysis, or let's say mathematically, a basis transform signifies a change in the coordinate system within which the tensor is described, and we could use a change in this coordinate system for many different applications, many different purposes, some of which we'll get into later. But for certain types of problems, it can be easier for us to visualize, understand a problem, and also perform certain operations if we shift our point of view or shift the coordinate system used to describe the problem. And let's say, well, I use the term mathematically here, but let's say mathematically or theoretically, it expresses the tensor's components in terms of new basis vectors that account for this change of perspective. The change of basis process is fundamental to physics and engineering. We will see that a lot. It facilitates the interpretation and analysis of physical phenomena across different coordinate systems. Now, this is one slide that's trying to address a pretty complex problem or pretty complex issue. So forgive us if it's not the most robust, but I think the main point that we're trying to convey here is, well, first, the basis transforms can mean lots of different things. One of them being a change in perspective, or another one being, some sort of remapping of the problem to make it easier to understand. And second, it's a very useful tool in many types of scientific, let's say physics or engineering related problems. And that's the reason why tensors are so powerful as compared to just a traditional matrix. So, as seen previously, a transform matrix like that below, right here, allows us to redefine our axes or our reference frame. And so here we have a little bit of an example. Again, we're using rotation. So a new basis set, which I'm calling B sub new, is defined in terms of the old, which is B sub 3D. And so we already know how we're going to have to name our forward transform matrix, right? Because if we have B new times B 3D, that means that our transform matrix will be F 3D, F new, if we're assuming that we're sticking to that same notation. And so what we've done is we've taken the second and third axes and rotated them counterclockwise by some theta degrees around the vertical axis. And this forward transform matrix you see right here applies the rotation. That's only part of it. So what we're going to see is that this forward transform matrix is actually composed of two sub matrices, and we can do that, right? We can create a single forward transform as the product of some number of individual transforms, and that's what we've done here. We really have two forward transforms. The first is the rotation, and the second is the scaling. Now the second matrix, you can see all it really does is compress the units along the second axis by 2. And that's the reason why if you look over here, you can see that the tick marks on the darker blue axes are closer together than the tick marks on the lighter blue axes, because we've compressed that scale. And so by taking the product of the first and the second forward transform matrix, we create the overall forward transform matrix F superscript 3D subscript new, and that allows us to take the axes represented by the orange, the light blue, and the light green, and transform it to the orange, which stays the same, the dark green, and the darker blue. Now, we've spent a lot of time talking about how to transform the basis. And we largely already knew that before coming into this section. But what about the coefficients, right? That's an important part of this. If you remember, we know that a vector must be equal to its basis set times its coordinate array. Now, if we transform the basis, and I'm just going to call this 1 and 1, to a second set, the coordinate array has to respond similarly if we want to keep the vector constant. So we have to understand not only how to apply the transforms to the basis sets, but also how to apply them to the coefficients or the coordinate arrays. Some repetition up here. We said already, right, the vector v arrowhead must remain invariant to change of basis. As such, the coordinate or coefficient array transform is dictated by the following equality. And this is pretty similar to what I have written down here. Essentially, we have some vector. We can put it in terms of pre-transform basis and coordinates or post-transform basis and coordinates. However, these must be equal in order to maintain the primary characteristic of a tensor, being that it's invariant to change of basis. Now, if we take this equation and we rearrange it a little bit, we end up with this down here, which essentially says that our post-transform coordinates are equal to this product here of the basis times our pre-transform coordinates. Now, I'm not going to show this explicitly, but if we go back 1 or 2 slides, you can see we've already observed that this product is equal to the original backward transform matrix. I mean, we could find that if we go back here. Where is it? Let's see. Right. Here we see that the pre-transform and the post-transform basis equal the reverse transform matrix. And so if I were to move that over to the other side, we end up with B pre, B post inverse equals B post pre. Okay, so hopefully that's what we see on the next slide. And so, right, you can see same thing is listed right there. Okay, so now that we understand why this definition is consistent, we can say from these observations, we observe that the contravariant coordinate array obeys transformation rules that are opposite to that of the basis. In short, whenever we apply a forward transform to basis, if we want to get the corresponding coordinate arrays, we apply the opposite transform. Okay, we apply the reverse. Now, one thing you may notice is that the subscripts and superscripts here no longer line up the way that they did before, right? Now we have post as the superscript and pre as the subscript. That notation is only consistent for the basis. So if we're looking at transforming basis, you see the superscript aligns with the input and the subscript aligns with the output. So pretty much everything that's related to the forward and reverse transform is defined in terms of the basis. And we simply adapt those rules to apply them to the coordinates. So again, right, these relationships are opposite to that applied to the basis. And, we can see here 2 examples of transforming from the pre to the post coordinates, as well as going from the post back to the pre. And here we use B and here we use F. Now, there's a question asked right here. Are the meanings of the forward and backward transforms reversed when we talk about the coordinates or the coefficients? And the answer there is yes and no. I mean, I guess you could say yes, they are reversed. But I would say in a truer sense, no, they're not reversed because they were never defined with respect to these coordinates anyway. They were always defined with respect to the basis, the covariant basis. And so the meanings The definitions aren't reversed, they're just not defined in terms of those arrays. This next module introduces the second type of tensor that we're going to discuss in this course, referred to as the dual vector. The dual vector represents a functional relationship between a primal vector and a scalar value. It's somewhat analogous to how we generate a scalar value as the product of a row-oriented and column-oriented array. We're going to also discuss the dual space in similar terms to the primal space, which we discussed earlier, which we introduced earlier. A link to that next lecture is available in the description below, or will be available very soon. I look forward to reading your questions and potentially some corrections in the comment section.